right, today we are going to look at the relationship between moles. So that's our quantity that we talked about last time, the mass of a substance, and also how that can relate to the number of particles. So last lesson, we looked at how to convert from moles to particles and particles to moles. Now we're going to introduce how mass of a substance is related to it. So I've entitled this Working with Moles. You have the note that can go along with this if you'd like to fill in as we go. And if not, you can check the filled in version attached in the last couple pages of the note. Okay, later today, I'm going to have you attempt a gizmo that should help consolidate the information that we're looking at. But I like to use this little picture, this little clip that I have from the gizmo itself, because it kind of shows us the importance of being able to relate the mass of a sample of substance to amount in moles. So if you could imagine I had a single individual atom of copper, we could find the mass of that atom. And we have already talked about this in our first unit with isotopes. And the mass of a single atom of copper would be 546 units. That's the average mass of one copper atom. Average mass presuming isotopes. We've accounted for all of those. Now, the problem is, I'm looking at whatever this thing is, we don't really have a device or an instrument where we can just put an individual atom on and then find the mass. And even more than that, how are we just going to get one individual atom? So this is a nanoscale view. We don't have a tiny nanobalance to put individual atoms on. So oftentimes we don't work with, in chemistry, or anytime you have a sample of a substance, we don't work with just a single atom. We're going to work with many, many, many atoms. And that's where the mole became important. If I had, let's say, copper, this copper powder, which would be pure, it's still just made up of copper atoms, rather than trying to put a single atom onto a balance, which is going to be impossible, we can't do that. What if I took, rather than one atom, I took a mole of copper atoms? Now, if you recall from the previous day, and hopefully you listen to the song, a mole is 6.0221 times 10 to the 23, or I think we just stopped it at 6.02 times 10 to the 23. So if I had a mole of copper atoms, that's how many individual copper atoms I'd have. And if I dumped that onto an actual balance, like an electronic balance, like the one we would have in our lab, we'd find that the mass of a mole copper atoms is 63.546 grams. Huh. 1 mole. There's its mass in grams. And over here, 1 atom. There's its mass in atomic mass units, or we denote that with the U. So hopefully we're starting to see a relationship here. So we have another quantity we're going to introduce, which is called the molar mass. And let's just break that down into the two parts of that term. Molar, meaning I have 1 mole, and the mass. Now, if I had an atom of carbon-12, I'm going to work with carbon instead of copper. An atom of carbon-12, one single little one, would have exactly a mass of 12 atomic mass units, or 12U. If I took an entire mole of carbon-12, 6.02 times 10 to the 23 atoms, and put that on a balance, it'd be big enough for us to actually measure, we'd find that it has a mass of exactly 12 grams. So the molar mass is simply the mass of 1 mole of any element or of any compound. So this means that 1 mole of any element has a mass that is numerically equal. It is the same as the element's atomic mass, just shown in grams. So I've given you an example here. If you have your periodic table or your textbook and you flip to the back and you find your periodic table, what I want you to do is look up sulfur. Look for that capital S. If I had an individual atom of sulfur, we look at the mass number on the periodic table and I'd find that it's 32.07. So 1 atom is 32.07 units. And that would be the average atomic mass, right? We'd calculate that from all the isotopes. Now, instead of having a single atom, if I take an entire mole of those atoms, my cat's going bananas in the background, I'm sorry. If I had an entire mole of atoms and put that on a balance, it would be 32.07 grams. Okay, same value. It's the same mass number. It's just a different unit when I have an entire mole of the substance. Okay, let's use oxygen. Average atomic mass is 16 units. That would be for one atom of oxygen. If I had a mole of oxygen atoms, that's 16 grams. Okay, and again, for lead, we look up the mass number. There it is if there was one atom of lead. But then if I have an entire mole, 6.02 times 10 to the 23 atoms of lead, it would have a mass of 207.2 grams. Okay, I'm going to pop out of here for 1 second. You've got your periodic table. I thought I'd just use an online one, but we could do that with any element. So let's say I want to find gallium, the terminator metal. Look this up. Its atomic mass, 69.723. They're a little more precise on this table than ours. For 1 mole, it would be 69.723 grams for a mole of gallium. Flerovium, you say? 289 grams for 1 mole. Bromine, 79.904. So you just simply have to look at the mass number, and that will show you, what its molar mass is. Okay, see, here's a mole. There's the mass of 1 mole. Now, the unit that we use to report this, it's a mass that we've measured in grams, but we're going to be even more specific and say that that's grams per mole. Or I could imagine that like per 1 mole of the substance. Not for 2 moles, not for 3, not for half of a mole, but for 1. Now, if we wanted to find the molar mass of a compound, we can look at what elements comprise that compound. So to find the molar mass for not an element but a compound, we're just going to simply add up the molar masses of the elements it's composed of. So let's use an example with carbon dioxide. I'm sorry, I couldn't get my 2 here to go subscript because it was already subscript. So what is the molar mass of CO2? Now, when we denote molar mass, rather than using a little m, because in a lot of our classes, even grade 9 chemistry, or maybe you saw it in physics, we often use a lowercase m to represent mass. We're going to use a capital M this time to denote, yeah, it's a mass, but more specifically, a mass for 1 mole. We have to make that variable different than just a lowercase m. So on the molar mass of CO2, what I'm going to do is add the molar mass of carbon, and just one of those, plus 2 times the molar mass of an oxygen. And I'm going to use times 2 because in CO2, there's 2 oxygens. So what I've done here, I've looked up on my periodic table. I'd go out and find the atomic mass, the mass number for carbon, and it's 12.01. The unit I'm going to use is grams per mole, molar mass. And then to that, I'm going to add 2 times the mass of oxygen. So 1 oxygen, 16 grams per mole, and I have 2 of those in my compound. When I add them together, the total molar mass of CO2 is 44.01 grams per mole. So if I had a mole of carbon dioxide, it would be 44.01 grams. I've given you a harder example here, lead nitrate. Again, sorry about the subscripts. So what I've done with this one, I've just broken it into the individual elements, lead, nitrogen, and oxygen. And in this compound, I have 1 lead, 2 nitrogen, because this little 2 outside of the bracket, times 2, and then 3 oxygen times another 2. There's 6 times the molar mass of oxygen. Plugged in my values, 1 lead, 2 times the mass number or molar mass for nitrogen, and 6 times the molar mass for what we'd find in our table, the mass number for oxygen. You're going to add all of those together. Try this yourself. Grab your calculator. Make sure you're doing your order of operations correctly, and it should be 331.22. The unit, molar mass, grams per mole. and that would be the mass for 1 mole of lead nitrate. If I look at these two values, the mass of this is much, much larger. That makes sense. This is a much larger compound than CO2. Okay, so with that kind of tool in mind, we can then convert from moles to mass and mass to moles. Because realistically, in our laboratory, we don't have some device called a mole meter. We can't just take a pile of sugar and dump it onto a device and it just reads out how many moles it is. I pour it on and it says 0.1 moles. That doesn't happen, but we do have electronic balances, which can tell us the mass. So with the rest of this lesson, we're going to try and relate mass to moles, moles to mass, and then actually try to link it to what we did with our previous lesson in particles. So at this point so far, you know 2 important tools or pieces of information in quantitative chemistry. The mole is super important to chemists. First thing we know, in a mole of particles, there's 6.02 times 10 to the 23 particles. The second thing we know now is the mass of a mole of any type of particle, whether it be an element or a compound, is called the molar mass, and we can now find that using the atomic masses from the periodic table. So from here on out, we can convert from mass to moles or moles to mass if we use the value of molar mass. And I'm going to show you a couple examples. So here is, well, here I would say are the 2 key formulas now that we have or are working with. I'm going to introduce a new one, which is little n, which is the amount in mole. It's still the same mole we talked about in our last lesson. I can find it if I know the mass of a substance and I divide it by its molar mass. From the previous day, another way that we can find moles is by taking how many particles we had divided by Avogadro's constant. In practice, this new formula that I've just shown you is far more useful. I mean, how often do we actually count the number of particles? This is more of a formula we kind of use to help us conceptualize what the mole is, but this is one that we often use in practice, how we know the amounts that we are reacting, perhaps. And this is what we're really going to focus on kind of from here on out. So N is the amount in mole. Remember, MOL, that's the unit, kind of like G is for grams. MOL is for moles. It's much, much shorter. No. Little m is the mass of a sample, and we're going to measure mass in grams. Capital M is the molar mass in grams per 1 mole. And from the previous day, capital N is the number of particles. That could be measured in atoms, molecules, or F units, formula units. Depends on what we're talking about. Is it an element? Is it a covalent compound, or is it ionic? And Na is Avogadro's constant, which is in 1 mole, that's equivalent to 6.02 times 10 to the 23. So there's 5 key variables we now know. And it's so great that they are all N's and M's. That's not confusing in the slightest. But we're going to show you how we can use those to help us convert from different forms. So I have posted this. This is on your note as well, but this is just showing our relationships. If I know an amount in moles, I can change it into mass. If I know mass, I can change it into moles. If I know moles, I could use that to find the number of particles, or if I know the number of particles, I can use that to find the amount in moles. So we're going to work with those variables to help us. Okay, so there are 3 examples that I'm going to go through. Here's the first one. You had a sample of carbon dioxide. Now, I'm going to hope that you know at this point that that is CO2. Sometimes the question may not give you the formula for a compound, but if it's an easy one, I hope we can find that, or just using your tricks from nomenclature. So let's say you have a sample, 0.75, 3/4 of a mole of carbon dioxide. What would be the mass of this sample? Whoa, just kidding. Go back. So what I'm going to do, we'll use, again, I'm looking for the asp of grass, but let's put down our G's and R's. Let's write down what we know. And this might be a good idea, again, to have a cue card beside us. And maybe you're going to add another one with our new formula that helps us denote what little m and big M are. So I know mole. So you're going to look back. What is that? That's little n. What mass? What am I trying to find? So the mass that I'm trying to find, that's little m. I don't know what it is. And if I stop the question there, I don't know anything else. However, I actually do. I know that it's carbon dioxide. So what I can do is go to my periodic table and find 1 carbon, 2 oxygen, add those together to give me the molar mass of carbon dioxide. So even though this wasn't stated in the question, I found this using my periodic table and because I was told what the compound is. Notice I've listed units with each. So capital M, that's grams per mole. So I'm asked for mass. I'm going to take my equation N equals M over M and rearrange it. So mass is the number of moles times the molar mass. Here's my amount in moles. Here's my molar mass, and we're going to multiply them together. Look at my answer. This makes sense. I don't have an entire mole of carbon dioxide. I have less than a mole. This value tells me 1 mole is 44.01 grams. So the mass that I should have here, since it's not quite 1 mole, should also be less. You'll then notice in my final answer, I've rounded it to 33.0. And where did that come from? Well, I'm looking at this value here that has 1, 2, and that 0 on the end still counts, so 3 significant digits. Remember, the leading 0 is not significant. Here, I have actually kind of used a rounded value, so I would consider that 4 significant digits. Not necessarily a constant like we saw with Avogadro's constant, but I would consider that 4. But when I multiply, it's the fewest number, 3 significant digits that I've rounded this to. Okay, now we're going to go the opposite way. Use molar mass again. So how many moles of acetic acid, which is CH3COOH, I didn't group all of the C's and H's and O's together because often in organic chemistry, this is how we see it written. It gives us a hint as to what its structure is actually like, how the atoms are actually arranged. But here's acetic acid, and there's one that I don't just presume you know the formula for, so I've given that to you. How many moles are there in a 23.6 gram sample? Okay, let's read the question. How many moles? N. I don't know. Mass, 23.6 grams. So you should get used to matching your unit to the variable. Now, molar mass, I want you to try this. You're going to notice with all of mine, I don't show all of the work. Okay, I'm going to flip back a couple slides to where I showed this full calculation. I don't need you to show that to me. If you can plug the values from the periodic table into your calculator and give me a molar mass, that is all I need to see here. But I want you to try this. How can we find this for acetic acid? So I have 1, 2 carbons, 1, 2, 3, and 4 hydrogens, and then 1, 2 oxygens. I want to know the amount in moles, so I'm going to use my formula, mass over molar mass. Plug in my values. Divide. Rules of division, fewest number of significant digits. So here I have 3, and here I have 4. Here's my answer, but then I'm going to round that to 3 significant digits in my therefore statement. Let's look back at this conceptually. A mole of acetic acid is about 60 grams. I only have 23.6, a little bit more than a third of 60. So when I look at that value, yes, that makes sense. Okay, now the last thing we'll look at are two-step calculations. So that's basically using this new formula that I've shown you, N equals M over M, and how I could then use that information to convert to particles. So if you also use Avogadro's constant, once you find an amount, let's say in moles, you could then convert it into number of particles. Or if you had the number of particles, you could change it into moles. And then if I know the molar mass, change it into grams. Okay, so here's our last example. I think last two examples. What's the mass of 5.67 times 10 to the 24? That's more than a mole. Formula units of cobalt 2 chloride. And this is where I'm testing your nomenclature. We're going to use our crisscross trick. COCl2 is the formula. Okay, let's write down what we know and what we need to know. And you're going to notice my givens and requireds. It's fine if they're mixed up. You don't have to put all the givens first and required second. So what is the mass? M. I don't know. Of this many formula units, I'd look at that and say to myself, those are particles. Tells me how many of them. So there's my capital N. Of cobalt 2 chloride, COCl2. Well, it doesn't say it, but I could look at my periodic table, add up 1 cobalt, 2 chlorines, and I could find its molar mass. And then the fact that I also have the number of particles, this tells me, maybe Avogadro's constant might be useful. So I'm going to write that in as well. When I start writing down capital N's, it's a good idea to have the NA value reported as well. And if I'm starting to write down little m or capital M, make sure both of the M's are included. So let's see what I know so far. I have N and Na. I can use that to help me calculate the amount in moles. So here I've just plugged in my two values. I want you to try this. Type this into your calculator. Make sure you're getting the correct value. And if not, hop on the meet. Let me know. We'll help with some calculator issues. So my first step, I found how much that is in moles. Moles. Yeah. And I haven't rounded it yet. I want to keep about 5 digits. Don't round until the very end, or else you get something called the compounding error. So that's my amount in moles. I just gave you a given required list here, so we didn't have to keep flipping back. Okay, so now that I know my amount in moles, little n, is there a way I could turn that into a mass? There is, or else I wouldn't ask you. So I'm going to take that amount in moles and let's change it to a mass. So multiply them together. Here's my final answer. I haven't rounded it yet. And then in my therefore statement, I'm going to go back to the fewest number of significant digits. And in fact, it's the fewest number that I've used throughout both of the calculations, since I'm just multiplying, dividing. So if I look at my given required list, you're going to notice Na is a constant. With my molar mass, I've given 5 significant digits. This capital N, the number of particles, that's 1, 2, 3 significant digits. So I'm going to round my final answer to 1.22 times 10 to the power of 3. And the reason is, by going to 1, 2, 3 sig digs, I still have some values after I've rounded that too. So I'm going to use scientific notation to help properly express that, rather than writing out something like 1,220, 1220, which then might look like it's 4. So this really clearly tells me that it's just 3 digits. Okay, I want you to take a look. I don't know why that random period is there. I want you to take a look at the last one. It's determine the number of molecules. That's N. In water. That's H2O. We'll come back to that. In a 10-gram sample. That's a mass. So how many particles do I have in 10 grams? There's 2 pieces of information that are not shown there, but we can find them. Avogadro's constant. Notice here I've put the type of particle as molecules, and then I've got my capital M here, which is molar mass, and I would find that from my periodic table by adding up 2 hydrogens and 1 oxygen. With the information I have, the first thing I'll find is moles, because I have little m and big M. So I can use that, divide and find the amount in moles. And I'm going to keep a bunch of digits. I'm not going to round just yet. And if I know the amount in moles, I can also find the amount of particles. So my second step, going back to our first day's calculation, I've taken that molar amount times Avogadro's constant. Okay, here unrounded, but that's how many molecules I would have. And my final step, I've rounded it to 3 sig digs because of the mass, which was 10.0. Okay, so that kind of takes care of how to convert between moles, mass, and number of particles. But the big thing that I want you to kind of focus on here is really that I've only introduced one new formula. I've only introduced this mass and molar mass. As I said, using perhaps some cue cards or just some separate space, some sort of reference sheet, while you're practicing these, it's a great idea to write down what each of these symbols, which each of these variables represent, because they're all n's and m's, and that gets really, really confusing. So I'm going to ask that you try. I've just picked out a variety of questions from the text, and if you have any questions, please pop back onto the Meet, and I can answer those there.